All right, here we go. So we're going to break this lesson into two parts. Today is going to be the entire lesson. There's some homework there, 1 through 14. And then 9.5b will just be a complete total practice on this. So hopefully by the end of two of these lessons, 9.5a, 9.5b, you got this idea and concept rock solid. All right, so new idea, inscribed angles. Remember, we're going to do many concepts today, but remember the basic ideas that we've been dealing with. Well, each individual thing that we're going to do today is easy. You put it all together, it can be slightly confusing. So make sure you do it slowly, make sure you pay attention, make sure things go in your book of truth. All right. Remember, I said this before, I showed the same slides. The rest of the chapter, lots and lots and lots of stuff. All right, recall that we've been dealing with circles. Center of a circle, if you go outward from the center of a circle with two segments, you make a central angle and you make an arc. So we have central angle, angle 1, and we have minor arc AB. And minor arc A, or the relationship between the central angle and the arc that it forms, is that they are not congruent because they're two separate things. One's a curve of a circle and one is an angle, so they're not congruent, but their measurements are equal. So angle 1 has a measurement, and the amount of the circle covered in arc AB is also a degree, or a measurement measured in degrees. And angle 1 and arc AB are equal to each other. Okay, so here comes the new stuff. So going back to that other idea right here where the central angle is, and I mentioned this before, so this is the central angle, but the angle can be drawn in many different places. So the vertex of angle 1 is at the center, but I could place that vertex anywhere. I could place it outside the circle. I could place it inside the circle, just not at the center. And then the one that we're going to talk about today is what would happen if I place the vertex on the circle. You get something that looks like this. So this is going to be the angle that we deal with today, angle 1. Well, it's not a central angle because it's not the center. It's not outside, it's not inside, it's on the circle, and it has a name, and its name is called an inscribed angle. Now, remember, we had the word way back from the first section of this chapter, inscribed shapes, and that's the shape on the inside. And remember, that shape fits snugly inside of a second shape. So we have an angle fit neatly inside a circle, so the angle is called inscribed. So here's the actual definition. It's an angle whose vertex is on the circle and its sides are chords of the circle. So there's two different inscribed angles there. And notice the black lines that make up the angle are actually chords of the circle. Two segments whose endpoints are on the circle. Now, the so what for this is just like it is for a central angle. Inscribed angles actually describe arcs. Angle 1 is a minor arc, arc that's made by angle 1 is a minor arc, and the arc made or formed by angle 2 is a major arc, but both of them are arcs formed by inscribed angles. All right, also recall that the relationship between the central angle and the arc it forms is that they are equal. Well, that will not be the case with inscribed. There is a relationship, but they're certainly not equal. So in order to show you that relationship, I'm going to do a proof. So the question is angle, or the measure of angle B and arc AC, are they equal? I've just told you that they're not. So what should go right in between? We're going to get a formula from this. And well, you can kind of see the formula right here. So it turns out, and I got to prove this, that the arc, whatever its measurement is, take half of it, and that's the angle. So angle ABC, or just plain old angle B, is equal to half of the arc it makes as long as angle B or ABC is an inscribed angle. Now I got to prove that, but it's actually pretty simple to prove. All right, so there's my setup, and that's where I'm going. So let's see. It's high school. We're in a geometry class. We're going to make triangles. So I'm going to make a triangle there. And initially, you would think I'm going to connect A to C. I'm not going to connect A to C. I'm actually going to connect A to O. In other words, I'm going to make a radius OA. So there's my radius, such as construction. And now, wait a minute. If I made a radius OA, well, OB and OC are all radii as well, too. I'm going to ignore OC for a second and just look at OB. So if OA and OB are both radii of the same circle, then they must be congruent to each other because all radii of a same circle are congruent to each other. Now, if OA is congruent to OB, there's the tick marks there. Look at the triangle. Well, we've got an isosceles triangle. And I know that in an isosceles triangle, that the angles opposite the congruent sides are congruent to each other. So that means angle A and angle B are congruent. Now, I'm going to call them slightly different names, but I'm talking about angle A and angle B. I'm going to call angle B ABC, and I'm going to call angle angle A, BAO. You'll see why here in a second. I could have called angle ABC, ABO, but I'm going to actually call it ABC. You'll see why here in a second. All right, so angles opposite the congruent sides are congruent of an isosceles triangle. All right, cool. So now I'm going to look at each one of those angles, but I'm going to do some labeling first, right? If they are congruent, then it turns out that angle AOC, look at where angle AOC is. Angle AOC is an external angle of triangle ABO. And we know that the exterior angle of any triangle is equal to the sum of the two remote interior angles. That would be angle A and angle B. So AOC is equal to angle A plus angle B. But wait a minute. In the previous statement, we said that angle A and angle B are congruent. So I can pick either one of them. I'm going to suspiciously choose angle A and say that two angle A's is equal to AOC. But that statement right there comes from the fact that the exterior angle of a triangle is equal to the sum of the two remote interior angles. Okay. Now, why did I call it angle A and not angle BAO? Because it's simple. Notice on my formula, what I have there on that previous step, I have two measures of angle A is equal to the measure of angle AOC. So if I divide both sides by 2, right, now I'm going to call it ABC, right, because remember, it's the same angle as angle A and angle B are the same angles. So ABC is the same as angle A. And I divide both sides by 2. That's a substitution and just simply a little bit of algebra or division, right? I'm just dividing both sides by 2. And angle A is the same as angle B. I'm just going to call angle B ABC. All right, cool. Now, angle AOC is equal to central angle, so therefore it's equal to arc AC. And now I'm done with the proof. Why am I done with the proof? Because if AOC is equal to arc AC, then I just do a quick substitution for angle AOC there, and therefore I get that it's equal to half of the measure of arc AC. Quick substitution, and we're done. We're kind of lost in what we just proved there, but here's what we just proved. If this is the shape that you get, or this is the shape, or this is the shape, these are all inscribed angle, that the angle, that would be angle B in each one of these cases, or ABC, is equal to a half of the arc it makes. In other words, half of AC. So that is the formula, and that is the relationship. Now, you have to have an inscribed angle, and that means an angle whose vertex is on the circle. But if that's the case, then that angle, the inscribed angle, angle B there, in each one of those examples, is equal to half of the arc that it makes. What arc does it make? It makes arc AC. It could be a major, it could be a minor, it doesn't matter, but the angle is half of the arc. Okay, so usually the challenge of this is just remember, what am I taking half of? Am I taking half of the arc, or am I taking half of the angle? You will always be taking half of the arc. If you wanted to say this in the opposite direction, if they gave you the angle, then if you double the angle, double angle B, you get to arc AC. All right, hard to remember which one. Here's how I remember it. If I have a semicircle, in other words, a diameter, and I make an inscribed angle to the points A and B, so I'm going to connect C to A and B, it's kind of easy to see by observation there that angle ACB is actually 90 degrees, just by observation. That's how I always remember. And then I think, oh, arc AB or arc ACB would be 180 degrees, therefore the angle is half of that. So that just keeps track of me of which one is half, the angle or the arc. And it's always the angle that's half of the arc. All right, these are going to be a little bit messy. You'll get a hang of them after you do a few of them. All right, that is a really messy example right there. It turns out this is pretty simple. Remember, we have that technique in geometry where it's really messy is to declutter the picture. So in your mind's eye, I want you to get rid of everything but what's written in red. Everything but's written. So I'm just looking at the circle and the red. And if you notice, we have an arc PQ in red, and it's listed as 40 degrees. Well, from the previous theorem, we know that the angle that makes that arc, and that would be angle T, right? And that's labeled as at the value X degrees right there, is equal to half of the arc. Therefore, X has got to be equal to 20 degrees. Now, ignore all the red and look at the blue, except that we need a little bit of the red there. So if you look at the angle that's blue, it's 50 degrees. And if you look at the arc it makes, that would be careful, that would be arc PR. Therefore, arc PR would be 100 degrees. And therefore, well, half of, or not half, but a little bit of that arc of arc PR, PQ is 40. So if we subtract 40 from 100, we in fact get 60 degrees. And so that's angle Y. A little bit messy, but if you declutter the picture, it makes sense. All right, ready for another idea. So think about this. I got an inscribed angle. That's angle 1. And on this, I'm going to make the picture really messy. I'm going to do another inscribed angle. This one's blue. Now I'm going to make the blue disappear and reappear. And each time you should notice that the arc that angle 1 makes and the arc that angle 2 makes are exactly the same. Well, if that's the same, that could only happen if angle 1 was equal to angle 2, and that's the next theorem. It's a corollary, so it's a corollary to the previous one. And it basically says that if two angles form the same arc, that would be arc AB in this picture, then they got to be equal. Okay, so that's corollary 1. Next thing, so think about this circle. This is going to be the picture I showed you before, but this is a formal theorem / corollary. So if you have a semicircle, then I don't care where you put C as long as C is not on A or B. Put C anywhere on that circle and then connect C to A and B. I just put it at the top, but I can put it literally anywhere and it's going to make a 90-degree angle. Why? It's inscribed. And the arc that it makes is a diameter, or it forms a semicircle arc, and half of 180 is 90. And that's corollary 2 to 9.7. Notice they've got their C, they call it X here, in a different location, but you can just, by observation, you can see it's 9 degrees. All right, so that's the result or that's what the so what is about corollary 2. All right, moving right along, last corollary, not the last thing, but the last corollary today. So circle, and this time I want you to make a quadrilateral. Now you could do this off on your own, all by yourself, draw a circle, and then I want you to make a quadrilateral. That means a 4-sided polygon. I didn't say to make a rectangle, I didn't say to make a square, I didn't say make a trapezoid, I just said make a quadrilateral, any one that you want to, as long as all the vertices touch the circle. Now, you're going to find out that you can't make a parallelogram do that. You can make a trapezoid do that. You can make a square or a rectangle. You can't make a rhombus do this. You can make just a plain old quadrilateral. There's mine right there. It's not a trapezoid. It's not a parallelogram, rectangle, square, rhombus, any of that. It's just got 4 sides. And it's a polygon. So here's the interesting thing. Now, here's what corollary 3 says. If you look at angle H and if you look at angle F, so if I look at angle H and I look at the arc that it makes, so follow the red lines from H, and you can see it makes arc GE or EG. That's part of the circle. Now look at angle F and look and trace its lines. It makes the rest of the circle. So it makes major arc GHE. So look at angle F and it makes the arcs GHE. Well, that's the whole circle. Therefore, if you add those 2 arcs up together, you get 360. And we know the relationship between arcs and inscribed angles is half. Well, that means that angle H plus angle F added together must be 180. And we would call those angles supplementary. So that's what this says. And it says in words, it basically says, if you choose an inscribed quadrilateral to a circle. And if you choose opposite angles, it's got to be opposite. It can't be adjacent angles. It's got to be opposite angles, H and F, G and E. And if you add their sums together, you get 180 for the aforementioned reason. I kind of gave you a proof there. So G plus E is 180 and H plus F is 180. And we're talking about the measurements of those angles. All right, one theorem left. I'm going to do some practice work here. This is a really messy picture here, but let's see if we can do it. So I'll do some illustrations here, hopefully. There's lots of places to start here. We got to find angle BCA. So let's find angle BCA. So if I trace out BCA, that's from here to here to here. And there's nothing listed there for, I mean, there's nothing, question mark right here, nothing listed. But if we trace out the red, we see it makes this arc A to B. And now we see, is there any inscribed angle that makes AB? And we see, in fact, I need another color for this. We'll go back to blue. We see that that is also this angle right here. So angle D also makes that same arc, right? And if angle D is 40, right? If angle D is 40, right? Then therefore, the arc has got to be double that, right? So did I lose myself here? Let's are they doing BDA? No, they're doing that one. So BCA is equal to BD. Oh, I'm sorry. I was talking about the measurement of the arc. So apologize there. So the arc itself is double 40. So it's right, darn you. I'm giving you too much information here. Here we go. I'll get a handle of this. So the arc itself is 80 degrees, but that's not what the question is. The question is the angle, and the question was, I wrote a 2. Undo. I want a degree symbol. There we go. We want this question mark here. So the question mark here says that if both inscribed angles, angle C and angle D, make the same arc, they do, arc AB, then they must have the same measurement. So therefore, that means that angle BCA is also 40 degrees. Whew, there we go. All right. Let me clear that and start over again. All right, so ABC, which you can already see the answer there. So let's see, why is ABC, I'm doing this one right here. Why is ABC, A to B to C, why is it 90 degrees? Well, if you look at what it makes, or it cuts into this diameter. Diameters have 180 degrees, or in other words, this arc right here from here to here is 180 degrees, and the angle is half of 180 degrees, therefore it's got to be 90 degrees. Okay. Anything left? Yep, one more left to go, and that is BAD. So let's see, where's BAD? B to A to D. Well, we know that opposite angles, I'm just drawing an arc here, not to show congruence, but opposite angles, that one and this one, they're not congruent. Ignore the arc. I'm just showing you the two angles I'm looking at. They are supplementary, in order to add up to 180 degrees. Well, in the previous problem, we found out that this one was 40 degrees. So if that's 40 degrees and the other one is 30, 40 plus 30 is 70. That's horrible. Is 70 degrees. And since angle A and angle C would have to add up to 180, 70 minus 180 is 110. Therefore, I know that angle BAD is 110 degrees. Well, I kind of stumbled through all that, but I got there. Okay, last shape, think about this. So I got an inscribed angle. So let's see, angle T, since it's inscribed, would be equal to a half of arc AB. Now, imagine what would happen if I move point B closer to point T. So I'm going to move point B closer and closer and closer to point T. It's still an inscribed angle, so it would still have the same formula. Move it really close to T, and it's still the same formula. Move B so close to point T that it is point T. In other words, point B went away, and I'm just left with point T. And now AT is a chord but that other red line that makes up angle T is not a chord anymore, it's a tangent, hence the T there. The question is, would the formula change? And the answer is no. It would still be the same formula. I can move B as close to T as finely as possible, and it wouldn't change the formula. So what would change if B was actually T? Nothing. It's just a tangent now, but the formula would look differently. So in other words, it's still going to be angle T, right? But, well, there is no B anymore. So I can't say it's equal to 1/2 arc AB, but I can say it's equal to 1/2 arc AT. So it's the same basic idea. It's still it's not an inscribed angle, but it's a tangent. So you got a combination of chord and a tangent, but it's the inscribed angle formula. So if you have a tangent to a chord of a circle, then the angle formed between the chord and the tangent is equal to half of the, it says intercepted arc, big fancy words for the arc that it makes. So this arc that it makes right here, A to T, whatever that measurement is, half of it would be angle T. And that was the last theorem. So here's a quick example. We got a tangent, we got a chord, we got an arc that's 140, therefore the angle's got to be half of 140. It's got to be 70 degrees. Well, that was pretty simple. And that's it for this lesson. If this is usually where the students kind of end up having issues. Why? Because if you look at all of these examples right here, these are the classroom exercises, they're kind of messy. Some of them are pretty straightforward. Others of them are a little more challenging. A couple hints. One, declutter the picture. Two, always look for overlapping angles that make the same arcs. Look at question number 4 there. If you notice, X and Y make exactly the same arc. And then look at that one marked 38. Well, 38 is exactly the same. So guess what? X and Y are also 38 degrees. Look at number 6 there. We have that inscribed quadrilateral. So opposite angles are supplementary. So just whatever adds up to 180. We got those tangent ones for 7 and 8. And the only weird one is number 9. So what in the world is going on here with number 9? So let's see if I can explain number 9 here, because that's usually the one that gives kids problems. This is classroom, not homework. Let's see, I know that this angle is equal to this angle. Why? It's an isosceles triangle. So those are equal. And that means that the arc that they make, so there's the arc that X makes, there's the arc that Y makes, and therefore they must be equal as well too, but they're going to be double whatever angle X and angle Y is. Well, what's the other piece of information that we have there? The other piece of information we have is that this arc from here to here is 80. Well, I just described that these two arcs, the ones in blue, are equal to each other. From 360 degrees in a full circle, subtract 80 degrees. So let's see, 360 minus 80 is 280 degrees. So we know that between the two blue arcs, there's 280 degrees, and they're equal. So therefore, that means each arc there is going to be 140 degrees. Now, that's not the final answer, but each arc, because they're equal to each other, is 140 plus 140 is 280. And therefore, the angle is half of 140. So that means X and Y are 70 degrees. So that's just a couple, just to give you a little bit of idea of what the homework will look like. If you run into a problem, as always, just send me a quick email and I'll get back to you as soon as I can.